So as I've mentioned, switches are often used in modern Ethernet networks, as well as pretty much any sort of network now uses some sort of switch. And switches can come in different flavors. So we're going to talk about some of those details about switches. So they used to be hubs inside Ethernet networks, and the problem with hubs was that they didn't offer any intelligence, or very limited intelligence at that. So they were more or less acted as just kind of a connection interconnector. It just bonded copper to copper behind the scenes. And the problem with that was if one device tried to transmit while another device was trying to transmit, well, then you'd have a collision, and that's where CCNA CD came in. And so the more devices you had on a network, the more collisions you could potentially have, the more broadcast traffic would be on that network, and so on. So there wasn't an easy way to divide up your network necessarily. So switches give you the ability to have a collision domain between every port. And what I mean by collision domain is this. So we've talked about broadcasts, and broadcasts are based on what subnet you're on. So we'll talk about VLANs coming up with switching and how they help with the broadcast issue. But for collisions, as we're talking with the hubs, collisions are based on this idea of people being on the same connection, the same bus. And the old way of doing it was we'd have some sort of hub, we'd have a couple devices plugged into it. So these are our hosts, they're connected into a hub. The hub then goes and connects into another hub. And then that might have some sort of hosts on it as well. And then that might go and connect to another hub. And then that hub would have other devices connected to it. So when one of these tried to transmit, everyone else saw that transmission. When this one tried to transmit at the same time as this one, we'd have a collision. The data would go across the network, and then it would end up in some sort of collision here on the wire. It would explode in a big fiery mess. So then everyone would have to wait with that hold down timer that was mentioned for a certain period of time before they could then talk again. So it slowed down the network, and that's a collision. So when one device tries to communicate at the same time as another device. Now there is a methodology built into Ethernet where it's supposed to listen before transmitting, but that doesn't necessarily always work perfectly, so that's how we end up getting collisions, especially if you have a very large network and you're very far apart. So the way to get around this would be then to replace a hub with a switch. Or, back in the old days, we would replace this with one switch, basically. Whoops, hold on. So switches used to be very expensive, so they would only get replaced with every once in a while. So now we have a layer 2 switch. The layer 2 switch sits in between these two hubs. So what that effectively does is it creates one collision domain and then another collision domain. Every port on a switch is a separate collision domain. So that means these two hosts now that are connected as well, they have their own little collision domains. So now when one person talks over here and one person talks over here, then that only affects their hub. That only affects their side of the switch. And then when these two hosts communicate, it doesn't really matter because they go directly into the switch. So that's why switches are so very nice, is it minimizes your collision problem. So once switches became more affordable and all these hubs started to get replaced with switches, well, now we have this nice situation where everybody has their own collision domain. it's a switch, and that's a switch. And instead of having this as our collision domain, we now have this as a collision domain, this is a collision domain. Every single one of these is a separate collision domain. So this is pretty nice with switches. This is why they're so loved. Is every single port on every single switch is a separate collision domain. So that's why I was mentioning how CSNA CD really isn't much of a concern when we start getting into a lot of switches being used, because every single port is just a direct connection basically. So this host is directly into the switch, one collision domain. When he communicates the switch, if we have 3 devices here communicating at the same time, the switch will handle that, and it will properly multiplex that traffic out onto this connection. So it's not a problem. So this eliminates, the switches eliminate the problem of collisions essentially. So that's where they came to be. That's why they're so powerful. So, and then there's layer 3 switches as well, which we'll get into later, where they basically do routing. So we have a couple switch types. We have fixed switches and we have modular switches. So fixed switches, they don't have any method of configuring them. You can get them pretty cheaply. They don't do much besides just interconnect and do some basic layer 2 functionality. You can't go in there and manage them and change port configurations and change the duplex, change the VLAN associations, do these fancy protocols that we're going to be talking about coming up. They're very basic. So fixed is basic but cheap. So if you're in a small environment, that might be a good option for you. The modular ones are good for larger organizations, and there's kind of like a middle ground too that we'll get into. But the modular ones essentially are chassis based, and with the chassis design, you have a backplane that's usually a relatively large device, and then you'll have different slots in there that are available. So you'll have some sort of management slot, you'll have some sort of other type of switching slot, and you'll have all these available slots that plug into a backplane, and then this will in turn go into some sort of server rack. And then each one of these slots you can put some different card in. So this could be a management card, which will give you a management interface. This could be, you know, Ethernet with copper, and it could be 24 ports. This one could be fiber below it with, you know, some sort of connection. This one could be, you know, fiber with LC connections. Another card could be Ethernet, copper, 48 ports. But then this one could have been 100 megabit, and this one is 1 gigabit, for example. So you can mix and match to whatever makes the most sense for your business. Sometimes you can also, depending on what you get, you can also swap out individual ports. So individual ports that can be swapped out are called switch form factor pluggable modules, so SFP modules. These are found on almost everything nowadays, and even on some of like the fixed switches. And I mentioned there's one that's kind of in between. So you have fixed switches that are fixed config, modular switches that are chassis based, but then you also have managed switches which fit in the middle here. So managed switches, they come usually in a 1U form factor. They're just one slot. They're all by themselves. They don't go into a chassis, and they'll have however many ports you purchase. So, you know, if you bought like a 48 port switch or something like that, it's got a whole bunch of ports. And you can access this through some sort of interface like SSH, or through some sort of graphical interface, usually some sort of web-based GUI. Depends on who you purchase. And often there's uplink ports over here on the side. and these uplink ports are often Sfp modules. So these are a nice in-between because you have the ability to go in and manage them. You can do those nice things like setting specific VLANs on different ports and changing speed and duplex settings if you need to and things like that. And you also have the ability of changing out what kind of fiber connections or copper connections are used to do the uplinks. Some companies out there even use these as their stacking modules. So since I mentioned that, another thing you can do, the way these modular type switches work is that you have one managed card or two, and they manage all of those boards below it. So when you log into this switch, it'll say, this is board 1, port 1 through 24, and then this is board 2 / ports 1 through 12. And then the next one would be, board 3, ports 1 to 12 or something like that. That's the general idea. You can do a similar thing with these managed switches that are standalone. And sometimes they'll have specific stacking connectors and specific stacking cables. But sometimes some providers now, some manufacturers are creating them so that they can be stacked through their Sfp modules. So you can use fiber to interconnect them, and you could even stack them very far apart through different closets even, which is pretty neat. So if we had another switch here that was directly below it, for example, and I had some stacking, some Sfp ports, I could connect them together. And if I connect them together as a stacked switch, then instead of this being managed at this address and this one having to have its own management address, basically they become one, just like a modular switch. So you'd log into it at .10, and then this would be known as as device 1, ports 1 to 48, and then this would be device 2 slot, card 2 essentially, 1 to 48. So it allows you to more easily manage closets full of switches. So if you have 8 switches that are 48 ports each, that's a whole lot of stuff to manage. If you stack them, they can be managed more easily. And then also traffic in between. Usually this stacking cable is a high throughput cable. If you have a gigabit switch and it has 48 ports, so that's 48 gigabit per second, a lot of times that stacking cable is also 48 gigabit per second capable. So that way, if you have a number of people on this switch down here trying to access traffic either on this switch or further up the line all at the same time, the cable that interconnects those switches is able to handle that amount of bandwidth. So that's a very nice positive thing you can do, and this is actually usually at a pretty good price point where you can make this happen in a smaller company. So this is a good option for people that don't want to go into the whole modular chassis setup. And you still have that flexibility of those Sfp modules if you want to backhaul over a long distance with fiber or something like that. So how a switch works is it uses the MAC address to decide what ports to send traffic to. It builds a MAC address table and learns what traffic is coming from which ports. So whenever I send traffic across the network, that switch will then learn what port I reside on. So it'll actually create a table of saying this MAC address is on this port, this MAC address is on this port, this MAC address is on this port. And then if you have multiple devices on one port, for example this one here, switch in the middle, on this port with the explosion that's happening right now, it's going to know that there are 3 potential devices on that port as far as it's aware. So this port could be fastETH 0/1, and it may have in its table MAC 1, 2, and 3 are all on that port because it goes this way to this switch. So it just learns and builds a table of what MACs are on what ports. If there's no port in its MAC table for something that's coming into it, then it's going to flood it out onto all the ports except the originating port. So if someone on the left side here was trying to get to this guy over here, he's going to send his traffic through this switch, across this connection to this switch. This switch doesn't know this one's MAC address yet, so then it's going to send out a flood to every port on its side, asking, well, where is that guy? And then it's going to hit this switch, and then it will also forward it out. And then it'll contact this host and say, okay, it's this guy. We'll send it back. And this switch might not have done that if it already knew it was in its MAC table. If this switch already knew about it, then it could have just responded right away, and it didn't have to do this. But I was just showing how it could potentially cascade, and you might get flood after flood until it finds the destination it wants. So once that device responds, then it'll get added to the MAC table of each switch along the way, and all responding MAC addresses get recorded into the table. So anything that it sees coming across traffic-wise will get recorded into the table for a certain period of time. There's usually a timer involved where certain MACs will get flushed out after a certain period of time. Another nice feature of switches is they can automatically negotiate speed, duplex, and Mdi-X settings on the newer firmwares and models. So if you plug in somebody on over here on this port and someone over here on this port, and they're different speeds, and then maybe someone in the middle here is 1 gigabit, the switch can handle that, and it will automatically negotiate with that host. You don't have to go in there and do that. As one of the features of Ethernet and with the switches is we can automatically negotiate that. So it'll send some traffic back and forth and say, oh yeah, you can run at 10 megabits, that's great, I'll set my port to that. Oh, you want to run at half duplex or full? Oh, you can do full duplex. Okay, let me set it to that too. It'll handle that. And nowadays we also have the option, the ability to automatically switch that crossover. Remember, we're talking about MDI and Mdi-X. It'll automatically detect whether or not you're properly communicating on that port, and it'll try to switch it from MDI to Mdi-X to see if that helps. And if it does help, then it will leave it in that state. So it can automatically do a crossover for you. That's why I said it's not necessarily used all the time now, because you have this option, but it really depends on what version firmware you're running and what devices you have. If you have older devices with older iOS on there, it might not do this. But that's why it's always nice that you still have a crossover cable, but that is that option out there. So the MDI is for the routers and hosts, and the Mdi-X is for switches. So when you interconnect them, it'll automatically negotiate that now if you're using something modern. There's a couple different ways these switches do forwarding. One of the ways that I've been describing through the way Ethernet works and such is the CRC value. Remember on the trail, the tail of the frame, it'll have a CRC value that it checks about. That's called store and forward. And let me clear this out. So we have store and forward as one of the methods. It will read the entire frame. And then it does its own CRC, and it compares. If everything passes, then it sends it on its way. If it fails, then it drops it. Another method is fragment-free, another method is cut-through, one of them being fragment-free. There's two variants of this. Cut-through is a faster method. So store and forward, you can tell, is a little bit slower, and you have to buffer more information. You have to read the whole thing, check it out, compare the value, and so on. So with cut-through, we have two variants. The first one was fast-forward, and then the one that I just mentioned, fragment-free. So fast forward reads the entire destination MAC address. Remember when we were looking in Wireshark, you saw the destination MAC address right there in the beginning. It actually lists destination first, which is nice because then it doesn't have to read the source. It could just read up to the destination and then immediately act upon it. It'll then forward after reading the destination MAC. Fragment free, but the problem with fast forward is it's super quick. It doesn't do any sort of CRC check. It just immediately says, where are you going? Okay, go. And just boom, right out the door. Fragment free stores the first 64 bytes. Before forwarding it. It checks the destination MAC and then it forwards it. And the reason for that is because usually most errors and collisions occur in those 64 bytes. So the idea is it doesn't do a full CRC check. It doesn't do a full CRC check, but it checks those first 64 bytes. And if nothing horrible has happened to them, it'll check the destination MAC and send it on its way. But it ignores the need for buffering and viewing the entire frame and then doing that meat grinder CRC check at the end. So that's a more common, faster method of doing forwarding without having to go through the whole store and forward method. There's also two types of memory buffering. On switches, there's two optional methods. We have port-based and shared. So with port-based, there's a queue for every port. It can cause a delay for other frames, though, and other ports. One of the other methods that can be used is a common queue. Using the shared method. So there's a common queue for all ports. It's dynamically allocated to each port, which is nice because then if one port needs more or less, it'll do that automatically. And it allows for larger frames to be transmitted. So you'll probably see this more often, especially with SAN type technologies and needing to send larger and larger frames. The shared method is certainly preferred.